So this is benchmarking Node.js with statistics, and this is something I did for the Node core. Before I started working on this, we had a lot of benchmarks, but no statistics. And for me, it's been an interesting journey to figure out how to sort of express statistics for very simple-to-use tools. However, when you do this, you lose some level of details and understanding, and with that, I also believe you lose some trust. So hopefully we can fix that today. So who am I? My name is Andreas. I'm a math student. Particularly work on data analysis and machine learning, it's also called AI. And in my spare time, I'm a NodeConf contributor, where I work on async hooks. So those of you who are not familiar, async hooks is a new API that we are developing, which allows you to get notified about everything asynchronous. And so because it's Node and it's everything asynchronous, this is going to be one of the hardest code paths we have in entire Node core. So we want to make sure that it's very performant. And to do that, we use benchmarks. So here's a similar one. The ones that we're using are much more complicated, but the purpose is the same. Benchmarking after power, it's too short to measure, so we create a for loop. Then we do some alteration. Then we time it. Then we compare them. And find a winner. Pretty simple. So what I would like you to do now is to take part in this game called Recognizing Randomness. So here are two pictures. One is random, and the other is not. And so please raise your hand if you think it's the one to the left that is random. OK. 3, 2, 1. Final answers. You can lower your hands. And please raise your hand if you think it's the one to the right that is random. Many more. There's a lot of you who don't want to answer. OK, so what I see is about 70–80% of you think it's the one to the right that is random. Turns out it is one to the left. So I think what happens is that we see sort of clusters in the one to the left, and we see these clusters as correlations, and something that's correlated is not really random. But in fact, this is not correlated. So this behavior was researched by a behavioral psychologist called B.F. Skinner, who used pigeons. So here we have a pigeon who looks at the sign, and then it does something, and if it does what the sign says, it's rewarded by feeding it. So in fact, it learns to read. It's pretty good at this. Here we have a similar pigeon. This one turns around, is fed, so now it believes that turning around equals food. And we see it turns around again, but exactly the timer that goes off this time. It has nothing to do with what the pigeon does. It's just a timer. But now it really believes that turning around is amazing, so it turns all the way around. Still just a timer. So what B.F. Skinner saw was that pigeons are pretty good at correlating things when correlation exists. It very quickly learns to read the sign. However, when no correlation exists, it tends to see correlation anyway, so it gets some belief, it reconfirms that belief, and in the end, it becomes a superstition. That's what B.F. Skinner calls it. So what the pigeon needs to do is it needs to be much more critical, and that's actually also what we need to do. So let's be more critical, and what we can actually do in this simple example is that we can ask V8 to produce the assembly code. I'll print it out. And here it is. You don't need to know assembly in order to see that these are exactly the same. So obviously, the performance is the same. What we saw is just a product of randomness. So by now, you're hopefully starting to get convinced that humans, just like the pigeon, is pretty good at correlating things when correlation exists, or when no correlation exists, we tend to see correlation anyway. So what we need to do is that we need to be critical, and we need to replace this intuition with something so much more objective. And this much more objective thing, I guess you already know, is called statistics. So probably the most important theorem in entire statistics is what's called the central limit theorem. So let's consider a benchmark again. And in each iteration, we do some tasks. That's too short to measure, but let's say that we could. It would look like this. And what we do in practice is that we sum up all these times, but just measuring the time at the beginning of the for loop and at the end of the for loop. And then we divide by the number of iterations, and then we have a mean. That's what we see in the bottom. Now let's speed this up a bit, And what you see is that these means sort of send us around a specific point, and then they spread out a bit from there. And this is what we call the normal distribution. So a distribution describes how randomness behaves, and the normal distribution is the distribution of means. It has two parameters. It has a mean itself, so that's the top of it, and has a standard deviation. That's how wide it is. It also describes how random it is. So a bit more formally, we can say that any source that has a mean and a standard deviation, and we've got to be most sources, I will say, then if you take the mean of n observations from this source, then those means that will always approximate a normal distribution. You also know the parameters of the distribution. We know it has the same mean, and we know that the randomness, what we call the standard deviation, is downscaled by a factor of square root of n. So this is really remarkable, I think, because it allows us to say something so specific about something so general as in any source. Really remarkable. So we will use this, but before that, we need a bit of probability theory as well. So it's pretty simple. It's not the height of the curve that corresponds to probability, it's the area under the curve. So if you take like a 40% area, then that corresponds to a 40% probability of landing in the corresponding interval on the x-axis. Then there's this math trick where we can put the mean and standard deviation outside of the normal distribution. That turns useful later. And there's also some assumptions we should satisfy. It's called IID. Statisticians, they are crazy about them. Basically just restart Node.js after this benchmark and don't interfere with performance like watching a video when you get bored. So now we can talk about confidence intervals. So let's imagine that we have a web server, this is some performance, and one day our project manager comes to us and say, oh, it's too slow. We need to optimize it. Let's get it down to 0.1 second per request. I'll say, okay, that's fair. Let's do some optimization. Let's ensure this performance by doing some benchmarks. That's what we see on the top. And the question that we are now essentially asking ourselves is, do we believe that the true performance of this optimized web server is below 0.1? If it is that, then we're good. But it's really difficult to answer just from looking at these observations. So what we do typically is we take the mean, and now you know that the mean follows normal distribution. But we do not know the parameters of this distribution because it's real life. So what we can do is that we can estimate them. But when we estimate them, we introduce an error. But it actually turns out that we can mathematically compensate for this error. And that's quite remarkable. We can mathematically compensate for the error by using a t-distribution, which is remarkably similar but different enough to compensate for the error. But watch what happens when we increase the number of observations. Then we get more certain, and now we can ask ourselves, how certain are we? So it turns out that if you take the 95% probability, 95% area, then there's a 95% probability that the true performance, not the estimated, but the true performance is inside the corresponding interval on the x-axis. It also means that there is a 5% risk that is not inside the interval, but if you're not satisfied by that, just choose a lower number and you will get a wider interval. This is really remarkable because we don't know what the true performance is, but we can still say with some certainty that it's inside this interval. So it's been 8 minutes now or something, and you haven't seen any JavaScript code. This is even a JavaScript conference. Here it is. Calculate the mean, calculate the standard deviation, then you divide by square root n. This is what we call a standard error. And then we set up the student t-distribution. Now you see it only takes one parameter. So that's because we use this math trick where we put the mean and the standard deviation outside. And that's what happened in the last two lines. And then we have this t.inverse, which is pretty complicated. What it does is that it returns an x-axis value for when the area from -infinity to up to this x-axis value is equal to the input. So here the input is 2.5%, so we get 2.5% on the left and the right side. That way we have the interval. Now let's compare with our goal. So if the goal has been outside of the interval, then it would have been really easy. Because we know, if we accept the 5% risk, that the true performance is inside the interval. We know that. So if the goal is outside of the interval, then that must mean that the goal and the true performance are not equal. We can say that even though we don't know what the true performance is. It's pretty nice. And this is what we call statistical significance. But if the goal is inside the interval, then we're in trouble. Because the true performance is a specific point. There's nothing random about it. So it can either be above or below the goal. However, we have no idea which of those cases are true. There can be two causes of this. One is that we don't have enough observations, so we're too uncertain, or that the goal and true performance are actually equal. And because we cannot distinguish between these two things, we just assume that they're equal. But that's not at all the same as saying that they are equal. It's just something you say because we don't know better. So only if it's outside the interval, we can say it's statistically significant. So in NodeConf, we don't really have a product manager who comes to us with a performance goal. What we do have is a goal where performance shouldn't decrease. Or if we're introducing some optimization, then it must increase. So here we have two node versions. One is green, one is red, running the same benchmark. And what we can do is we calculate the confidence intervals. And that's what is in the bottom. And these intervals don't overlap. So that must mean that the true performance are different. If they were the same, if the performance of the two node versions were the same, they would have to overlap. But watch what happens when we decrease the number of observations. Then we get less certain, the interval starts to overlap, but it's actually still significant. We can go even further, and then it does become not significant. So it turns out that you can allow some overlapping. And there's no good intuitive explanation for this, I think. What I can say is that when we're considering them separately, we lose information about the standard deviation. So what we need to do is we need to consider them combined. So brace yourself. This is what's called the Ttest, and it does exactly that. It considers them combined. And it does that by not considering the true performance, but the true difference in performance. It's pretty complicated. There's a lot of math going on here. But I gotta say, it is a remarkable test because it's very robust, it assumes very little, and it does exactly what I said. It compares the true difference in performance. But while it's quite complicated, the concept, the structure of it is very much the same as what we did before with the one confidence interval, comparing with the goal. That looked like this. So you see, if we go back, that the structure of it, it still has a fraction, it still has a t-distribution, so the structure is very much the same. It's just the parts that are more complicated. So if we can calculate the parts, and this is pretty simple programming, I think, then the rest, which I think is complicated, is the same. So we calculate the standard error. This is the denominator of the fraction. It's much more complicated now, but it's still just the standard error. Then we calculate what's called the degrees of freedom. And this is just a fancy name for the input parameter to the student t-distribution. And then the rest is the same. But now we don't have an interval of true performance, now we have an interval of true difference in performance. So when considering an optimization, we want to make sure it does exist. Then we should make sure that 0 is not inside the interval. If it's outside of the interval, then that must mean, if you can accept the 5% risk, that the true difference in performance is not equal to 0. So it must exist. We have an optimization. That's great. So this is what we did. Created a data collection tool that satisfied these IID assumptions. Then we created a data analysis tool, which does exactly what I said. Uses the Ttest and calculates the relative improvement and figures out whether or not that's significant. So we indicate that with 1, 2, or 3 stars. 1 star means a 0.1% risk, or 3 stars means a 0.1% risk, and 1 star means 5% risk. So before continuing, I just want to show you that statistics go so much more beyond these very controlled cases like benchmarking. So we can also have a production server, and this we cannot really benchmark, but we can monitor the performance over time. And what we are interested in is these performance spikes that we have. And what we can do is we can calculate the mean performance of this web server. But now it's not just a mean, it's what's called a moving average, because it's moving over time. And it's still an average, so we can still calculate an interval. It's very similar to before. And then we can compare our observations with this interval. And if they're outside the interval, then they're quite unlikely. So we can mark them as red. So while these tools are, I think, pretty easy to use, there's something that's very difficult to put into them. And that's what's called preventing p-value phishing. So you don't know p-values, so let's just call it significant phishing. And there's this amazing XKCD cartoon that explains it. And I'll try to enact that. It's very embarrassing for me, but hopefully you'll enjoy it. So quick, jelly beans, they cause acne. Whoa, scientists must investigate this. This is how it happens in real life. Well, you can all relax. Okay, there was no correlation. It's not statistically significant. Wait, it could be specific colors. Now we really must investigate all the colors, pale, brown, pink, blue, teal, goes on. It's green, that's significant. So now we can publish a paper. The news gets over the paper. Everyone knows, stay away from green jelly beans. They cause acne. It's pretty serious. So while it may be true that green jelly beans causes acne, we have to be aware of this 5% risk. This 5% risk that we only got a statistical significant result because of randomness. In reality, there's no correlation. That is not a problem if you do just one experiment. However, here we do 20 different experiments with different colors. With the benchmarks, we do hundreds of thousands of benchmarks with different parameters. So in this simple case, we have 5% times 20. That means that we can mathematically expect one of these experiments to lie. It's pretty bad. We can mathematically prove that statistics is going to lie to us, on average. It's a pretty big problem, and statistics is broken, people in fact say, and it kind of is, but it's not like it promises more than delivers. It promises 5%, and that is exactly what it delivers. We just have to be very critical of that, and not just choose 5% because it's fine. So a simple solution, this is not the best, I think, is to take the 5% and divide by 20, and that way the total risk, use that as risk level in each experiment, and that way the total risk will be 5%. That's much more acceptable. And so, finishing off, I just want to summarize this, and that is that you shouldn't really focus so much on math. I think be aware of the IID assumptions, but beyond that, once you have the implementation, it's just 2 lines of code. You don't really need to memorize the Ttest in order to do this. What you should focus on is that you don't get into the belief that you can distinguish pattern from noise, because you can't. The pigeon looks very silly, and trust me, you're gonna look just as silly when you try this, and we do it every day. For me, this has been one of the hardest pills to swallow when doing statistics. Really get into the zone where you assume nothing. So use statistics, and when you use statistics and you see that something is statistically significant, also be very critical of this. Because there is always this risk, this 5% risk or whatever we choose it to be. It always exists, no matter how low we choose it. So what we need to do is we need to be critical of these results, and the only way to do that is to use our knowledge of performance. So use your knowledge of performance to be critical. It's very important. If you can do these 2 things, then you'll be an amazing data analyst. Thank you.